Hello, welcome everyone. I'm Jeff Brock, the director of the Data Science Initiative. It's a real pleasure to see you all here tonight. And it also was a pleasure to see so many of you at the campus launch earlier today at the roundtables. I'd like to thank all of you who participated. I think we took a great step forward in accomplishing our goal of building a broad campus network of collaboration. We had roundtables led by a broad group from across the campus, the Humanity-Centered Robotics Initiative, the Brown Institute for Brain Science, the Physics Department, the Joukowsky Institute, a whole range of leaders. And they emphasized the essential interdisciplinary nature of our effort here in data science, and indeed how the rise of data science is transforming the way we think about intellectual inquiry across the academy. And indeed, the Data Science Initiative here grew out of, I like the term, sort of a transdisciplinary convergence. We realized that computation, mathematics, and statistics needed to be woven together to address the fundamental challenges of data science: data curation and collection, causal inference, pattern recognition, artificial intelligence, just to name a few. Indeed, our core departments of applied mathematics, biostatistics, and computer science were already deeply engaged in the data project, as it were, and the affiliated group, Center for Computational Molecular Biology, which grew out of those three departments, became a core partner recently and was a real triumph of this. If anything, the math department, the pure math department, was sort of the Rip Van Winkle of this team, waking up to the fact that suddenly in Silicon Valley, people were talking about things like geometry and topology and harmonic analysis. And we thought, well, we better get to the table. But deep data exploration was not new to the campus. It's been going on all over the place, whether it's CLIPS, IBIS, physics, BCBI, all those acronyms that you hear. We just needed an organizing principle. And so while our planning chose to initially emphasize the core foundations represented so strongly here, we knew our effort needed to expand outside of these boundaries and engage the entire campus. We met with many different groups in the planning phase and then spent some time setting up shop. With a one-year master's program just launched, designed by our top faculty and being taught by them, a new NSF Tripods Institute grant just funded, and our home on the 9th floor of the Science Library buzzing with student activity, I think we're at last ready to go, hence the launch event you're all here attending. So the rise of data, its prevalence, its analysis, its power to influence science and society is all too evident in our modern lives. Our team at Brown felt we should be playing the long game, focusing on quality rather than quick wins in the data war. We thought Brown should leverage these quantitative strengths to build a foundationally rich research enterprise in data science, along with new curricula focused on methodologies, domain applications, and societal impacts, which should be our signature. But another important aspect of data science at Brown is the liberal arts ethos and its emphasis on helping students reach their goal to do good in the world rather than merely well. I organized a faculty forum last May with my colleagues Ur Satentamel, Joe Hogan, and Sohini Ramachandran, entitled Data Science as a Liberal Art. And it's easy to throw that term around, but I use the term carefully. The liberal arts involve education that builds our capacity to understand the world around us. Indeed, mathematics and basic science, as well as the social sciences and the humanities and the arts, form the core of the liberal arts. We believe that Brown should play a defining role in providing this lens of liberal arts on data science, and that there has been such enthusiasm in engaging with these data challenges across the campus gives us all the more evidence that Brown is the right place to do this. And indeed, here we sit in the nerve center of the arts at Brown, where next semester we'll be celebrating a joint hire between the Brown Arts Initiative and the Data Science Initiative, a deep scholar and artist I've known for many years. So while I want to thank also the Arts Initiative for hosting us here, I want to give them a chance to just make a couple of remarks. So I'm going to welcome Kira Del Sesto to the podium for a minute.
Good afternoon, everybody. As Jeff said, I'm Kira Del Sesto. I represent one of these other acronyms here, the BAI, the Brown Arts Initiative. We're very thrilled to have you here in, was it transdisciplinary convergence? Is that what you called it? So we've got another one. Again, super happy to have you here. The Brown Arts Initiative is another new initiative at Brown. We launched just in March. And since that time, we have been reaching out not only to other arts departments, but to groups like DSI to bring interdisciplinarity back here into Granoff. So as Jeff mentioned, we are going to partner on bringing Ali Momaini, who is the data science and arts professor of the practice, who will join us in January. And we're really looking forward to having Ali based here in the Granoff in studio, working with data science and arts students. I wanted to bring my best wishes from our director, Butch Rovan, who really wanted to be here tonight, but is in the air at the moment. But he asked me to convey his best wishes to you for a really successful launch and a wonderful day. You know, some people might wonder why data science and creative arts are able to work together. We at Granoff like to say that we are not just a home for creative artists, but for creative thinkers. Many people might not think that data scientists are creative thinkers, but I think we all know in this room you are among the most creative thinkers. So again, really welcome. So happy to have you, so happy to be working with you, and good luck.
Thanks, Kira. Just one or two more quick remarks. I would be remiss if I failed to mention that as novel as the idea of the data revolution appears, Brown's legacy in this area goes back many generations. And the late Ulf Grenander, former professor of applied mathematics here at Brown, was the architect of the subject of pattern theory. By understanding complex patterns in images from a combinatorial, statistical, and probabilistic point of view, he laid the foundation for computer vision, medical image analysis, and robotics. And if only he could see it now, with powerful new computational systems and architectures and statistically robust algorithms, new methods from deep learning relate speech to text, kinetic motion to brain activity, climate data to new climate models, to say nothing of the triumph of AlphaGo. The tools are now teaching the experts. And yet the experts agree that deep learning as a theory is in its infancy. Why does it work? The models of the previous century, largely driven by calculus, were great for building bridges and ships and getting us to the moon. But we're asking new questions. Can we design models of intelligence? How do they function? What is their reliability? Will our workforce become obsolete? And how can we ensure that the data used to train them are free of their own bias? As Google, Amazon, Facebook, Twitter marshal data at their scale and formidable computing power, how can we engage these resources in pursuit of open science and transparent intellectual inquiry? So our goal is to create a space for this dialogue. I'd like to transition quickly to the main event, but first I'd like to extend my gratitude to the extraordinary support of Provost Rick Luck, who wanted to be here today but could not, and President Christina Paxson, and the rest of the administration. Their encouragement and blessing of our interest in working collaboratively has provided a remarkable opportunity for all of us to explore beyond the walls of our normal disciplinary silos. I'm confident that this vision will be one of President Paxson's most enduring gifts to Brown, and I'm thrilled to have her here with us tonight.
So thank you, Jeff, and good afternoon and welcome, everybody. It's great to see you here. This is a big event. This is a big deal. This is the launch of the Data Science Initiative. It has the feel of something that is potentially transformative for Brown, and I'm excited about it. I hope all of you are too. Before I say anything else, I want to recognize just some, and I know I can't get them all, some of the people at Brown who made this possible. I recall sitting in my office around a table a couple years ago, and it wasn't that long ago, with chairs of 4 of Brown's strongest departments, then chairs. Jeff Brock from math, Ur Shententamal from CS, Konstantin Getsonis in biostatistics, and Bjorn Sandstetter in applied math. And this core group had come together with this idea that they were going to work together across departments and in collaboration with colleagues from around the university to develop this new initiative. And you know, the first step at Brown is, okay, you want to do this, put together a great proposal. And they went off and very quickly and very efficiently, maybe you'd done it already, I don't know, came back with a great proposal. And so we were off. This core group, again, in collaboration with many people from around the university, have developed and conceptualized what I think is a tremendously exciting program. I do want to thank Jeff especially for taking on the leadership of this program. His work has resulted in a very bold vision, and it's a shared vision and one that I'm very excited about. I also want to thank Andrew Moore, who I will introduce shortly, for being here today to deliver the keynote, and all of us are looking forward to hearing your remarks, so thanks for coming. So just a few words about what this initiative means for Brown. And, you know, I think back to a cabinet retreat that we had over the summer where we had leaders of different initiatives, academic leaders at Brown, come and talk about what was happening in their worlds. And I can see many people here in this room who spoke to us that day. And Jeff made this dazzling presentation on the DSI, which builds, again, on these long-standing strengths at Brown, but is integrating them and taking them to a new level. And, you know, he highlighted just the enormous potential of data-enabled research and learning, and he described some of DSI's early progress and accomplishments so far. So, you know, we learned, for example, about ongoing work using algorithms trained from large data sets of CT images to develop 3D mappings of traumatic brain injury. We learned about remarkable research taking place at ICERM, which is our NSF-funded Institute for Computational and Experimental Research in Mathematics, directed by Brendan Hassett and founded by our VP of Research, Jill Pfeiffer. And, you know, the data science research that's being conducted there is extraordinary, and the work just last summer is likely to yield 7 new publications in the field. We learned about the new master's program in data science, and I can tell you I've been talking to a lot of students, Brown undergraduates, who are now eyeing this as a 5th-year option, so watch out, they're coming. And they're excited about it. And, you know, we were reminded of these successful recruitment of people like Ali Momeni, a gifted scholar and artist who uses machine learning to explore aesthetics and sound design and musical invention. And, you know, one of my great excitements is just watching the types of people, the types of great scholars and researchers and teachers who we can attract to Brown because of the excitement of this initiative. So, you know, no question, this has already hit the ground running. It feels actually, in some sense, like a launch. You've been doing a lot, but we should have a launch. It's the right thing to do. And I think it's important to note that strengthening Brown's capacity in this area, taking advantage of the data revolution to advance knowledge and discovery, is central to Brown's strategic plan, building on distinction. It's written about in there in, you know, very few sentences, but you can really see the seeds of it having been embedded from faculty discussions that happened 4 or 5 years ago and are now coming to fruition. The Data Science Initiative is Brown's definitive response to a seismic change in how we confront data in the world. And this isn't just happening at Brown, it's happening everywhere. And it matters a lot, because the advances it will introduce in how we gather and curate and understand and deploy data are exploding the research landscape in higher education, and they are transforming industry, and they're creating new opportunities for research and industry to work together, which is also very exciting. The mathematical and computational tools that we're unleashing on every kind of intellectual inquiry, and the breadth is extraordinary, holds the promise of new methods of research and order of magnitude insights into, you know, pretty much anything when you think about it. At Brown, these insights are guiding us in developing a computerized framework for identifying and cataloging potential therapeutic uses of plants, thereby encouraging biodiversity. They're enhancing efforts at the Large Hadron Collider to discover new particles of the early universe by using algorithms to classify signatures in high-rate collisions. And again, blending another strength of Brown, theoretical physics with data science theoretical and experimental physics with data science is really exciting. Outside of Brown, but with some Brown involvement, we're doing work divining the patterns and provenance of Shakespearean plays via feature frequency profiling, which is a text mining message. So data sciences and the humanities, very much something that is generating exciting work. So all this is going on. What in an overarching way, does DSI mean for Brown? What do I think it's going to do for this university? And I think there are three things that I want to highlight. The first is that it expands the capacity of Brown scholarship to have impact in the world. And impact is something that we care a lot about. We're doing work that is going to catalyze work in brain sciences that help us analyze the massive amounts of data that are coming out there and help us move on to treatments and cures for conditions like ALS and Alzheimer's. If we can do that, that's impact. And it's this kind of powerful outcome that is really, propels, I think, a lot of people in this area to do their work. Second, the DSI affirms and confirms Brown's collaborative approach to advancing knowledge. And Jeff talked about this a little bit. We have a number of these hubs of knowledge, research, education across the university. And this one will focus on foundational methods in data science and their application in virtually any field. So the ability of this initiative to connect and collaborate across the university are really quite outstanding. And then finally, I do have to bring it back to our students. So third big impact, data fluency is really important. And the DSI ensures that data fluency will certainly be more than just a simple regimen of tool-based skills that students learn. Those are important skills, but they're going to depreciate quickly over time. But I think what they're doing is inspiring students to think about how the applications of data can be really a core competence for innovation, for discovery, for application in areas ranging from medical research, but also in areas like public policy and civic engagement. And this is something that I know excites Brown students very much. So, my hope is that every student who comes into Brown takes one of these great courses that you're developing, maybe in connection with another department at Brown, and leaves this university really understanding the power of data and the need to understand data science methods to some degree. So let me wrap up. This really is a milestone day for the university. I think that this initiative positions Brown for leadership in the field. It opens up opportunities to connect us to industry going forward. And it is sort of the essence of what we want out of the building on distinction integrative themes by marrying rigor with implementation, enriching our very distinctive approach, liberal art-based approach to research and education, and improving the prospect for Brown scholarship to have a meaningful impact on the world. And that's what we're here to do. So I'm very happy about this effort. So with that, let me introduce our keynote speaker. I had a lovely conversation with him this afternoon. He is, in a word, passionate about the impact of technology and computer science and data on the world. Andrew Moore is a distinguished computer scientist with expertise in machine learning and robotics. His research has included improving the ability of robots and other automated systems to sense the world around them and respond appropriately, a theme that I hope he will touch on today. He's dean, so he still does research, but he's also a dean. That's pretty cool. He's dean of Carnegie Mellon School of Computer Science, and in that role, he presides over this growing suite of hubs that continue to mainstream data science and forge new applications. So these hubs include the Robotics Institute, the Language Technologies Institute, the Machine Learning Department, and the newest CMU AI, which provides a platform for ongoing research and education in the field of artificial intelligence. Now, his presence at Carnegie Mellon and in Pittsburgh more generally has accelerated the transformation of Pittsburgh into a magnet for tech growth and entrepreneurship. And, you know, speaking personally as someone who grew up in Pittsburgh during the very dismal, dark days of a dying steel industry, seeing what's happening there now is just amazing. So I'm just, it's remarkable to see what CMU has done. It's quite an accomplishment. And Andrew's been a big part of that. His experience as founder of Google's Pittsburgh office and now a mentor of tech talent has really helped to cultivate deep and productive economic links between the university and the greater Pittsburgh community, which is quite remarkable. In a New York Times piece this past July, Andrew said of the milieu at CMU School of Computer Science and around Pittsburgh's very dynamic tech sector that it is, quote, like being at Hogwarts. Now, I don't remember seeing many computers at Hogwarts. I did see a lot of magic, and I hope that's what you were referring to. And, you know, interesting and novel ideas emerge routinely as entrepreneurs and engineers and computer scientists and artists are working together in unprecedented ways that benefit the city and the region. So I couldn't think of anybody more appropriate here to help us launch our data sciences initiative. So with that, I'd like you to please join me in welcoming our keynote speaker, Professor Andrew Moore. Thank you.
Thank you very much, President Paxson, and I am, of course, honored and delighted to be here. I think what you're doing is indeed very important. It's important for the world as a whole that you're training an entire generation of students to be comfortable and competent with data. I'm also, one of the reasons I'm so proud to be here is because when I was in industry and looking desperately to recruit people, and I will talk more about the talent wars later on, we definitely had this experience that when you hired someone from Brown, you didn't just get a smart, genius-like person. You got people who could work with other folks and take on the really quite frightening responsibilities that you have these days if you're working in a major internet company, healthcare company, transportation company. We need our engineers who are running the world to be good, well-educated, general, well-balanced folks, because else we're all in trouble. So I have very great respect for what this institution is doing to create its various students. All right, so what I wanted to talk about today was the life of what seems to be going on in the world right now around the use of data. And it is becoming very competitive, and there's a lot at stake, both between countries, certainly between companies, and actually, if we handle this very badly, it can lead to a greater breakup in society when the rich technologists like ourselves educate our kids to be the next generation's rich technologists, and the have-nots who are not getting a decent educational opportunity end up not joining in our world. So there's many places right now where there's a lot at stake. And I'm going to just try to give a map of what we at Carnegie Mellon see happening here. So that's going to be the talk. I'm first going to talk about how the world of big computer science views the role of data science, and then we'll use that as the backdrop for discussing these important areas about the talent wars, the question of what happens with computation, the importance of privacy in data science, and then perhaps most exciting of all, what this could actually mean for the natural sciences. And needless to say, I'm very, very welcoming of interruptions with questions or comments. So it's much more fun, I think, for me and for everyone else. If I say something stupid, call me out on it. We'll have a very entertaining experience. So please do not be shy. We don't have to wait till the end for questions. All right. So here's a backdrop with a very Carnegie Mellon-centric view of the world. In 1965, Alan Newell and Herb Simon, two of the heroes in the history of Carnegie Mellon, were very interested in, now that we have compute engines, does this mean that we can start to simulate intelligence, use simulated intelligence for the human good, and maybe even understand intelligence? And the culture at CMU at the moment, there's 240 faculty in the School of Computer Science, are all being brought together still by this important notion that Alan and Herb gave to us. And the succeeding generations of heroes, people like Raj Reddy and Takeo Kanade and Tom Mitchell and Jaime Carpinell, have really helped us grow this area. All right, so here's where they stood. They looked at humanity, a good example of intelligence, and they said, what's really going on? 1, we perceive stuff. 2, we decide to do about what we perceive, decide what to do about what we perceive. 3, we act on it. So this is what you might call artificial intelligence pre-101. This is this big thing which has driven thousands of people in their careers over the last half century, understanding this stuff. And for the most part, it's gone well, but it went through a very circuitous route, and the security of its route is, in fact, what makes me so excited that you guys are launching this data science initiative today, because it is the most important component. All right, so let's talk about this. AI was bubbling along pretty well, even back in the mid-90s when computers really sucked in terms of computational power. Many new ideas have come along to help this understanding of how to simulate and maybe actually take advantage of simulated intelligence. And one of the key points, I think, was in '97 when Kasparov was defeated in chess. And this made us all think, AI is really here now, we're in good shape. So that was good. It's good for the computers, I guess, not necessarily for the humans. But that was 20 years ago, and we're not living in an AI-controlled world. So what actually was going on here? During this time period, many of us were really focused on this decide question of how we actually search. And with something like chess, we can exactly model predicting what's going to happen if I try to move a pawn forward. The pawn will be moved forward. So chess is one of a class of problems closer to puzzles where we have a precise model of the world. Of all the things that the computer has to worry about, it doesn't have to worry about predicting what happens next. And so, of course, we had wonderful algorithms and hardware to just say, if I do this, then this will happen, but if I do that, then this other thing will happen, and so on. Back in the late 90s, we would do that about 50 million times during a sort of decision process for a game of chess. But that was really what the algorithm was. And many of us in computer science worked very hard to disguise from the rest of you how easy this stuff is. We just program our computer to ask lots of questions and then choose the best. But to everyone's disappointment, this didn't continue to work. And of course, the killer was that unlike chess, most parts of the world, when we're automating a decision, we don't know if I do this, then that will happen, and if I do this other thing, then that will happen, and so forth. We do not have this model of the world to use. And so that was not just a small problem, it was a huge problem. Initially, the way that we were trying to implement this predict the next step was to hire software engineers to write things often called rule-based systems or expert systems to allow us to have a reasonable job at predicting what happens next. And in a few cases, like laying out a microprocessor circuit or scheduling inventory for the space shuttle, you actually did know pretty much exactly what was going to happen, and so you could use this. But so many interesting things, especially anything involving being useful to people, we were not able to predict exactly what was going to happen. And so that's when lots of us in the area of AI, we were almost like the passengers on a cruise ship when someone shouts, "There's a whale over there." Everyone rushed to the question of how do we derive models which allow our AIs to be able to predict the effects of their actions if we can't hand code them. And that was the huge growth period for machine learning. It was so important, actually, that pretty much everything else was kind of stuck until we solved this. And so many of us jumped into this and spent at least a decade, sometimes up to 2 decades, really trying to figure this stuff out. And fortunately, as the years went by, progress was being made here. And that is what's allowed us now to start having systems like a system which decides which web results to show you. When it's choosing between, usually it chooses between between 100 million to 1 billion different options. And for all of them, it predicts, given this person asked this question, what is the probability that they'll find this result useful? And there's no handwritten things there. It's been learnt from data. And throughout the transportation world, the health world, the financial world, the military, this trick of embedding something which can predict what happens next that's trained on training data has allowed us to do a much more effective perceive, decide, act system where the decide is driven by machine learning. So when we at CMU have to design curricula or design a way to organize ourselves so that we are covering every aspect of research that we need to, we try to understand how to break up the different disciplines that students need to know about, and we need to make sure that we're making moves forward in. And of course, in the technology world, we talk about these things as a stack. That is, there's a piece of technology which helps other pieces of technology in the stack above it, and this piece of technology is helped in turn by stuff below it. And the thing which had been missing for most of us in AI had been these layers related to learning from data. At the very bottom are the devices which power all of this, including the network sensors which allow us to do much more effective perception now than we were ever able to do before. And then on top of all of this is act and decide. And for this real dream of useful autonomous systems which are trying to either simulate intelligence or actually be used to make important decisions in the world, we need all of these components. And whether you're working at one part of the stack or another, you really need the other bits of the stack above and below you. That means everyone needs each other if you're going to build useful things here. You can't get away with a bunch of lone wolf geniuses trying to do their own thing. Like many other areas of technology, we're now so complex that we have to rely on other folks in the stack. So what I'm going to do now is quickly introduce you to the components of this stack. Many of you will recognize your own layer, but as we talk about it, the theme I'm going to try to really push is how we have to be helping the people above and below us on the stack. And the folks at the very top of the stack with the important use cases, and your president mentioned some important use cases of faculty working in the DSI, those are what give real meaning to everyone working further down on the stack. So let's begin at the device layer. The push there is to be able to sense the state of the world. The more you can sense it, the more information there is for the decide component. Good example of this is with computer vision and other sensors, now around about, it covers about 4 square miles of Pittsburgh. Our traffic lights are watching every car individually instead of just sort of counting traffic. And then the way that we schedule the traffic lights is a optimization problem where we can actually plan for the movement of every car individually. So at any given time, the search space for these traffic lights is now a few thousand cars all throughout a region of the city to work out what's best, to figure out what to do to help all of them based on predictions of where we think they're likely to go. This so far has, in this part of town, reduced drive times by about 20% and emissions by about 23%. So those are both nice results out of this. Another example, which is going to come to a theme to do with privacy and a potentially Orwellian future, but which is so cool, is the fact that thanks to improvements in cameras and other optical technology, we can do things which just a decade ago we never tried to do. So the question of looking at someone's iris, that sounds like a reasonably conventional thing. Some of our faculty working on the gimbaling system of a camera, which is able to move the camera very, very quickly to point exactly at one particular point, can now, it's now 80 feet away, zoom in and get an accurate picture of a person's iris. This is now under trial on military vehicles for being able to just look at everyone within about 50 foot of a military vehicle and identify them by iris. That's exciting, Orwellian, but exciting, and it's very interesting technology. The reason we can do this, again, is improvements in sensor technology. The frame rate of these cameras, the ability of the gimbaling to get exactly to the thing that you need to focus on. There's a picture of this beautiful thing. At the moment, it's rather large, but that's one of the next things we're going to try. Other examples, of course, are in 3D mapping, an area where Brown has very strong faculty as well. Here, part of the trick was primarily to do with the data processing layer, the ability to perform this operation called particle filter localization on small compute instead of having to send it to a server in the cloud to run the big compute. And a final example of this is something which has led to, whoops, let me get this going. I'm having trouble finding my mouse, there we go. It's a technique known as inverse reinforcement learning. So you have one of the giants of reinforcement learning on your faculty, Michael Lippmann. Inverse reinforcement learning is trying to undo all his work. And what it is actually figuring out what all the players in a scene, on a street or anywhere else, what their likely intentions are, so you can figure out what is the most likely path they're going to take. And then there are many use cases to do with noticing people who are doing very surprising things, given what we know about them so far, and also taking over control of vehicles in situations where there's likely to be an accident. So that's nice. We feel very happy at the perception level, but perception by itself is not usually very interesting. You've got to do something with it. And that's where systems, operating systems, people who design data centers, people who design chips are incredibly important, and they are doing essential data science research when they're doing this. Here's an embarrassing story. At Google, one of my jobs was to help build the big engine machine learning systems, the things which were actually having to deal at the scale of tens of billions of events every day. and we were very proud of the system we architected, and it was well worth it. We spent a lot of money with our machine learning system, but it was extremely good for the users, and it was very good for Google's revenue. And then, having built this amazing system, I came back to Carnegie Mellon, very proud of myself, and discovered that someone had built something with the same computational capabilities with 1/100th of the compute power. And this is billions of dollars worth of compute power. And it was a perfect example of why, and it's me who looks stupid here, it's a perfect example of why industry cannot survive just by pushing on by itself, throwing money at a problem and not looking at the crazy ways of finding some alternative way to solve the problem. In this case, in a nutshell, I'm not going to try to read this big slide. The key insight is that when you're doing big machine learning and you're doing all this stuff with distributed data, you don't have to obey the normal rules of a sensible computing system to do with putting the correct locks to make sure that the right message has gone to the right node at the right time. If you don't bother to do that, and you start to violate all the things we learned not to violate in operating systems, then the wonders of the stochasticity of the training algorithms that we're working with allow you to actually show that by the beauty of linear algebra, that as long as you don't make too many mistakes, you're still going to converge, and each of your atomic operations can be dozens of times faster. So that was a very interesting and important lesson, that low down in the stack, you have to have people always looking out for ways to improve that. Having this ability to train much more cheaply it's not only important for the small companies that could never have afforded to build a Google-size infrastructure. Within the huge organizations like the NSA, like Google, like Facebook, it means that folks who are trying to invent new things can suddenly run 100 experiments a week where previously they could only run one. And so the whole rules of the game change. So great respect to the operating systems part of data science. Now, as we move up, many people in this room are familiar with machine learning. So what I wanted to remind you here is that there's still big, wide areas of our modern day lives which are just waiting for someone to get round to trying out machine learning systems sensibly with them. And this was one of the really novel ones which took me by surprise about 18 months ago. After this, as we go up the stack, we come into many parts of statistical analysis. Many people arrange this differently. If you look at machine learning algorithms as the brute force thing where we write down a generative model of some kind and then we say, optimize the heck out of that, find me the maximum likelihood set of parameters for this data, or do a big particle filter or MCMC simulation and figure out something about these things. That's machine learning. Then you bring in the statistical expertise on top of that to help make fine-grained decisions. One example here, based on very accurate tracking of the patches of skin on a face, you can work out what the muscles underneath the face are doing, and then you can take that back to areas in psychology to do with facial action units, which are demonstrating certain kinds of emotions, such as we have a involuntary contempt action where sides of our lips go back very slightly if we have a feeling of contempt. And we can't usually even detect that consciously, but you can, with a high frame rate camera, get that. So one of the outputs from this was the ability now, when we are looking at a cohort of patients who are being treated for depression, in a science article 12 months ago, the authors were able to show that they can detect whether the treatment for depression is having an effect about 6 weeks before the physicians or the patients, in terms of indications from this very fine-grained analysis of facial action units. So that's interesting. Now, we're going to quickly go up the stack. When we come up to the decision support layer, the really interesting place is where you're not just dealing with a room full of statisticians and computer scientists. You now are bringing in the social scientists, the physicians, the law enforcement agencies. It's helping make sure that we have a system in place for making decisions like who are we going to interview when a crime has been committed. And I know that many of the things I'm talking about sound sort of frightening life and death type situations, but that is the way the world is going. We folks who are helping with data are also taking responsibility for helping in life and death decisions make the world better. In this particular example, it was an implementation by one of the master's students in one of our own data science master's programs, who got very interested in the question of facial recognition in escort ads on the big search engines, combining that with some other information to do with linking together pieces of evidence in a network. And this has now been deployed to a few hundred police stations around the country. At the moment, they're credited with about 100 rescues every year of folks who are involuntarily part of some sex trafficking or escort rings. So that's both an exciting outcome, and once again, it's not just this gang of people who built that layer. They are building on technologies further down the stack. So Eric Zing, who helped with the very fast implementations of big deep learning, he can enjoy some of the credit for this excellent use case because that's what allows the statistics to run at a reasonable rate. Now, I'm actually going to move outside the data science initiative now. And of course, it doesn't really matter to anyone whether it's something's officially inside or outside it. But I want to really emphasize how data is wonderful, but data helps us model the world in a way which then allows us to make decisions. And at the moment, we've been talking about humans making decisions, like law enforcement agents. But of course, many of us, and the dream of Herb Simon and Alan Newell was to have automated systems making decisions. And there, when we look at how we structure education and how we hire faculty, we break this top area into the infrastructure technologies, which are usually to do with searching and making inferences over the models that we've constructed, and then the end use cases. And it's important that we distinguish these two classes of end use case. The one which people usually think of when they think of AI is autonomy. And we have plenty of examples of situations where you have to build an autonomous system. If you've only got 1/4 of a second to make a decision on how you're going to manage an inevitable collision in a car, then the human consciousness or the human brain does not have enough cycles to actually do anything useful, whereas a computer can easily. If you eventually find you need billions of robots around the world helping with farming and agriculture because we have to make 10x the effective use of the available soil which is remaining on the world, again, with 1 billion robots, you can't have them controlled by people. They have to be able to act autonomously. But then there's the other part, which is the case where AIs are just helping humans. The simple examples that we're all familiar with are things like using GPS to help us navigate around, or, okay, Google, I need a new pair of sneakers, those kinds of things. So let's talk about what's exciting in the AI infrastructure piece first. These are some of the active areas which actually cross among many use cases and provide that layer down to the predictive models. Optimization is, well, it's funny, optimization is cool again. If you look at what goes on with retailers like Amazon, even folks like Google who are involved in logistics, and then certainly things like drive sharing or transportation sharing systems, suddenly everyone is looking to hire the folks who are actually comfortable building very large linear programs or integer programs. So dust off those 1970s textbooks on numerical analysis, because they're cool again. The next thing, which is very important, and is an area where we are investing because we think that both the commercial world and the military world has underinvested so far, is in safety. And here's one example. These are parts of a military system called the TARDEX system, which is a moderately clever AI system. It's only moderately clever because it has been due to go into deployment for the last 3 years. So it's not the most advanced thing. What it's doing is intelligent convoying. So you still have a human driver in the first truck. In the remaining trucks, they're autonomous. And that, of course, is a less difficult problem than general autonomous driving. The thing which has held this up from release is it's virtually impossible to test using any sort of industrial or military test procedures. Why? Because it's built on modules which are learning over time. And at the moment, we have almost no known technology, certainly not in academia, for coming up with performance guarantees for something which is going to be learning to improve itself. This is a threat. I've tried to emphasize carefully how so much of what we're doing to design the next steps of artificial intelligence depends on learning. And yet, in safety critical systems up to now, we've always insisted that our engineers and architects and biomedical folks come up with some kind of proofs of the safety or efficacy of that system. So this is a growth area for academics to work on. Some are doing it by statistical approaches to carefully designing experiments to try deliberately to fool a machine learning system. That gives you one kind of test guarantee, which is more of a statistical guarantee. And the other group are going back to an area which many of us remember from the past, formal methods, formal program proving methods, nowadays including geometry and the dynamics of a learning system to show that in the worst case, something bad can't happen. This image is related to work by Andre Platzer, who came up with a proof system for showing that the new FAA collision avoidance system, which is going into production this year, can never cause a collision. He tried to prove it, was unable to, and then discovered a whole set of bugs which have now been fixed. The next area where we're still worried in the world of artificial intelligence is what we call the knowledge network. When IBM won Jeopardy, it was based on scraping Wikipedia and a bunch of other general knowledge sources for facts where you can identify the entities involved in a question and then have a reasonably good chance of being able to look up any question about the relationship between pairs of entities. That was very exciting. That is exactly the architecture inside Cortana and Siri and Google Now at the moment. But we, outside of those corporations, are almost unable to do anything useful at the moment because we do not have the big databases of all the entities and relationships between them that we need. So a big push, this is actually happening in a couple of weeks in DC, is a group of companies and of academics and then some government departments that are getting together to try to take what Google and Amazon have done for their respective knowledge graphs and start to build them for all the other parts of the economy: financial, government regulations, healthcare, education. So one of the goals here is that instead of just being able to ask, okay, Google, where's a good place to eat tonight 3 miles from here, which Google can answer very well for you, to be able to answer a question like, okay, Google, is my mother going to be covered for her pancreas treatment if she switches to this new health plan? And to do that, there's very creative work needed to take each of the entities involved, put them into a structured form, which we can then build the answers to. Finally, I wanted to mention game theory. A similar kind of breakthrough to AlphaGo happened in February this year when Thomas Sandholm's algorithm managed to beat the world champions at No Limit Texas Hold'em poker, which was unprecedented before, and it put to play once and for all the idea that it's something to do with assessing human emotions, which you need to play poker well. Other areas where game theory is making a big impact, and it's based on machine-learned models, are in various forms of exchanges, such as the kidney exchange by Thomas, which are able to rationally put together people with different needs in a way where every participant is happy that they have the right solution for them. This is currently known to have saved about 300 lives since it was introduced by far more efficiently dealing with the question of, if I want to donate to my daughter, but I'm not compatible, can I do a deal with someone else in a similar problem? And if that doesn't work, can we do 3, 4, 5, 6, 7, 8 link deals, cleverly invented in such a way that no participant will want to do a different deal in order to get a better solution. Another important example, Amy Greenwald, a faculty member in your computer science department, I doubt she even knows this, but her paper on how to combat the rather dubious behavior of things called penny auctions, which were a big scourge on the internet for a while, was extremely important through a game theoretic analysis to help figure out better rules of the game, which are less predatory. Because I don't want to be coughing and wheezing all over you guys for too long, I'm going to quickly finish up with the top of this and then jump to our final conclusions. Here's a few things. Autonomy is very exciting, and this is an area where there is very few people with the skills. The kind of thing which goes on with autonomy at the moment is at this sort of level. You build a system, in this case it's controlling one side of this soccer team, and at this point the system has made the decision to send that defender to that position in order to get ready to take another goal, and it shoots and scores. So here's what's fun about this area. We've got a few hundred people around Pittsburgh who know how to build these systems, and it's an art. There is no science, there's no version of software engineering methodology for doing this. Folks know that you compose an autonomous system into a series of cascaded behaviors below them, which often talk to behaviors below them, and we all mix these systems together based on our experience in the past. So the big challenge here is how to systematize this so that we can have 2 or 3 orders of magnitude extra people able to participate in building autonomy. The final area are things like involved with humans' lives being made directly better by good advice from AIs. And of course, this is the big competition which Google, Microsoft, and Amazon are fighting over with each other for their spoken dialogue systems to turn out to be definitively better than the others so that they can start to be the entry point for people who want to use artificial intelligence. Among these kinds of things are these awful-looking snake robots, which are now actually performing surgery where they insert themselves through pretty much any orifice they choose to very quickly get to a place where they actually do need to manipulate the tissue, usually take parts out or implant things. Jeff Huang, another of your computer scientists, has been leading the way for understanding eye tracking, so that as we're building systems where we're trying to make people's lives better through the way they're using technology, we can actually try to figure out, for example, if the mouse, their finger, their eyes, and I hope eventually their expressions can help us more quickly optimize the performance of these things. Now, what I want to do now, I'm going to finish up with comments on these 4 fronts, the things which keep me awake at night. So the first one, in talent. There is a desperate shortage of people with the skills to work inside this large stack. So really, Godspeed to you guys for building this new master's program, and my recommendation is don't hesitate. Grow this as quickly as you can to 1,000 students a year. Here's one of the issues, and it's just in one area of network security. When we're at competition with the other major powers, and of course China is the one that we're most concerned with, it is very asymmetric at the moment. We have probably 2 or 3% of the folks trained to manually deal with finding exploits on the other side of the Pacific, and jumping in and taking over systems and defending ourselves from that happening. Literally, we're training hundreds of people a year to be experts in this, where we believe China is training tens of thousands of people. So the place where we're putting our big bet is in the automation of this. We're never going to win as a numbers game. So what we're trying to do with our much smaller number of engineers is build the systems which are automating the behavior of these other folks. So that is part of what's happening in these talent wars, is we've got far fewer resources, and so we're trying to deploy them on an extra level of autonomy and automation in what we're doing. Next, I want to show you this example by some of a nice product. It's pretty simple. It's a nice climbing wall system where it watches your progress, and as time goes by, it gives you challenges, which makes it kind of fun to try doing different things on the wall to exercise different skills. So it's good. It's one of hundreds of exciting new products using computer vision and some AI planning. The punchline of this, why this is an important example, is that this was built by a set of students who couldn't program 12 weeks before. And one thing that we're learning is that we don't have to rely on training up people to take 7 or 8 years of training through undergraduates and graduate studies in order to participate in this. Thanks to the design of a stack which has component technologies, nowadays if you say, and let me show you another example of this, I can talk while I'm showing it. Someone says, it would be interesting to try to train people in sign language the same way that we train people to dance in Dance Dance Revolution. They don't have to do a PhD to do that. They can download the limb tracker and the front-end systems for putting the compute into the cloud and build this, again, after modest amounts of education in how to build these systems. So this is another, I think, inspiring things when we're talking about the talent wars. The fact that we have this stack means that you don't have to be a god at everything in order to design and create new products. And really the punchline that I'm trying to really push heavily in this talk is that we all depend on each other. This is why it's so nice that you've taken superstar departments within your university and actually started to have them working together, because it's a complicated world when you have some people dealing with kernels of operating systems, other people doing sociological questions of how you make decisions, and other people building autonomy on top of it. No one can do all of this. You have to have multidisciplinary, or as was described earlier, double rainbow of transdisciplinary awesomeness, or whatever it was. There's one important question which we don't know the answer to, as to how should we be training folks in this talent war. Some universities have taken the very rational approach of saying, let's do horizontal slices in here. We're going to have a master's in computational data science, which is all about those lower layers of the stack. And so maybe Philippe does that, while Suba works on the AI infrastructure. On the industry side, when you're building a team, you usually want to have a team of only 4 or 5 people to build any piece of software technology. You really get diminishing returns after that. But when you choose your team, you really want people who can work together and bring together complementary skills. Part of the problem of this model is that unless your team is very large, you're not going to cover the whole stack. Maybe they can go and take off-the-shelf components from it, but this is not necessarily the ideal shape. This is producing a bunch of specialists. Another approach is to try to do big courses or master's programs which cover the whole stack, a little bit of everything. Then you get folks who can work together, but you don't necessarily, especially if you're fighting against another company or another government with very strong people, you don't necessarily have the skills ready for that. So this, which I'm sure many of you have seen before, this notion of T-shaped skills is what we on the software management side love to see. If we can find people who have been trained enough that they can respect the layers of the stack above and below them, willing to talk their language and work with them, but have their own specialization, that is wonderful. If I have to put together a computer scientist and a statistician who don't really know about each other, and maybe the statistician thinks, well, that person just hacks up stuff but doesn't really understand the math, and the computer scientist says, this person just talks in MATLAB, how can I even deal with them? That's bad. If, on the other hand, you have folks who understand enough to respect each other, take advantage of each other's strengths, then you can build a good team. Next question, very interesting one, and if you look at VC investment, you see this phenomenon. We're not sure whether the next wins near the bottom of the stack are going to come from hardware or algorithms. For a long time, it was algorithms winning each round. And that algorithms include the use of category theory and other very nice mathematical constructs from graph theory and topology. What we've discovered now, though, is that with the birth of deep learning, we actually have the problem that despite everything we've tried, it is the fast algorithms which are winning. So we'll have to see how that one ends up. Moving onwards to privacy, I can't encourage enough for us to work on this. One of our faculty members, Matt Fredrickson, has shown in a series of very careful studies of FDA experiments that the extent to which we increase privacy controls is good for privacy, but it is costing, in some cases, thousands of lives. And so the analysis of actually the privacy trade-offs, rather than just assuming that we want to have 0 privacy or 100% privacy, is an important question which is under-investigated at the moment. And finally, I don't have time to do this topic justice, but the question of using these autonomous and AI assistants in the natural sciences is very exciting. Part of the reason this is so important is that between them, the internet companies have invested tens of billions into the question of how to most efficiently gain market share, get people targeted to the right advertisements, and create campaigns, advertising campaigns, which have good outcomes. That is greater than the investment of the National Science Foundation in how to, and NIH in dealing with scientific experiments and how to most efficiently optimize those questions. if we take the sorts of technology that so many of us in industry have used for optimizing campaigns and apply that to optimizing compounds, we're very excited about what the future is going to be like. So that's the whole story. I was trying to show you the map, show you how we've joined everything together, really emphasize the beauty of what you're doing here at Brown to bring a bunch of disciplines together and sort of express my appreciation for what you're doing here. These references to everything you've seen will be available on my website on the FAQ page if you want to follow up on any of this stuff. But in the meantime, that's it. Thank you very much.
I don't know if we have time for a question or two.
If the audience does, you might go wrong.
Okay, so just if there's any quick questions. Yeah.
Oh, me? Okay, great. You'll repeat it?
Yes.
So, you had a stack there. And at the bottom of that stack was basically data acquisition, and there were metrics, things that you choose to look at. It's almost like the subconscious of the system. How do you make sure that the subconscious is representative of enough that's out there? That kind of depends upon what people choose to look at and what sorts of things they choose to look at and what metrics actually get designed. So, how do you...
Do you want me to repeat that, Chris?
Well, I think
Okay. Okay.
This is a really important question. It is, if we work so hard on decide and act, but our perception is actually tracking the wrong things, then we could be making very serious mistakes. A great example of this is actually in the web industry, where so much of our work was based on the assumption that if people click on something, we've shown them something useful. And that was the perfect example of the one thing you can easily get out of web analytics is what URLs people have clicked on. So you can optimize with that. But it didn't take long before we started realizing, wait, a short click followed by a back button is probably a really bad thing. So we should figure out what to do about that. But then we have to say, but is it a really bad thing? How short is bad? Then we have to use machine learning at this lower level to take stuff that we can observe in a user experience testing thing to try to figure out what makes folks happy or unhappy. In the big companies, and this includes now transportation companies, car companies, heavy equipment companies, there are now usually groups called user happiness groups or user experience groups who are actually devoted entirely to figuring out what is making our customers happy, want to return, and in some cases, even that question, how you make your customers return frequently to your service, is not necessarily doing what the customer needs.
one layer in the house out.
Okay.
That's for folks that had access to the internet and they're actively using the internet. There's probably a whole pyramid of folks below them that didn't have access, so you weren't optimizing your algorithms for them necessarily, is the point. So, that's the sort of thing that, you wonder about, because that's the hard-baked stuff, that zeitgeist that's kind of sitting at the lower layers.
Yes, so it would really help a lot of our products and services if we could get an actual measure of how much serotonin is in your brain right now. And it would really help me on designing useful talks to be able to afterwards analyze a video of everyone and say, this person was smiling, but they were smiling with pain at this point. And so getting that extra data would be great. A hellish possible future is one where the large corporations and the governments have that data and the rest of us don't.
Yeah.
Hi, Andrew. The project that you mentioned about this open knowledge graph,
Yes.
I think that's super exciting. And there's this piece that you will be able to accomplish there by using information from the public domain, where you build these entity relationships at a very large scale. But in order to do machine learning right, you also need the private information, which is something that Facebooks and Googles have, and we don't have. So is there a plan to somehow get a sample, some sample private information so that you can put the two pieces together and build something?
Yes, so for a real knowledge network, we have to, every record has to contain provenance information about who owns it and what their data rights are for using it. The frequent comment from the web companies is, we would like to supply such and such amount of information. For example, no one would want to not release information about for every food product that Amazon sells. It would love to have an open way to publish all the allergy reactions and other information like that, which can be for the public good. On the other hand, there's commercially important information which folks have suffered and spent a lot of money to obtain, such as artful images of flowing dresses that you're about to buy, where folks are still going to want to have data rights to that. Then there are probably some other information which is very valuable, such as how often do 14 to 18-year-olds visit this page 3 times in a one-day session, which it's really important commercially. It's probably not the main thing needed for the big knowledge graph types of questions. So primarily, I think there are basic facts, and then we hope there is an industry of folks doing proprietary versions for sale of decorated entities with further facts.
Yeah, Constantine.
You mentioned safety, and for many of us who work in medical, that's a very important question. So I wanted to ask, what's your crystal ball in the foreseeable future for safety? Are we going to be getting answers primarily from empirical testing, or are we going to be able to start saying that something that was built via such a predictive model, et cetera, has a chance? In other words, if we don't understand how neural networks, deep learning actually works. I mean, we do, but we don't. There's no way to predict whether if it's even monotone. In
Right.
other words, a system that I have is monotone. So it could go off the deep end anytime soon, but theoretically, we don't understand any of it. I see this in radiology. And everybody is scratching their heads. I mean, I think the thing you mentioned with the airplane and testing it and so on is how people are going at it. But that's a very highly dimensional situation. Are we going to get some kind of theoretical understanding of some of this? And if it doesn't look like it's in the cards for the next 5 years or 10 years, what is good enough?
That's a really difficult question. I would love to spend 15 minutes answering. Let me just mention a few quick things about it. If you can simulate the world of training examples, for example, in a good physics-based generator of scenes for testing out a self-driving car, is it able to notice a pothole in the road? That is something where physics are good enough that someone can write a full testing simulation to generate images to hurt this. And of course, there's many adversarial methods where someone can write a network to try to come up with plausible images which are most likely to confuse the primary learning system. So I think that if in an environment where we're able to say we can model the set of possible worlds, I'm pretty happy about that. But if you're doing something, say on the internet at the moment to predict who's going to buy what, for example, it's actually not uncommon for some big news event or a hurricane or Halloween happening on a Saturday to give a completely different set of data than anyone's seen before. That can result in poor predictions, but that's not such a bad thing. But it can result in the stochastic gradient updates starting to go crazy under some circumstances and actually have a big problem. That's okay if your website humorously suggests stupid products for a few days. It's absolutely not okay if suddenly a whole bunch of vehicles, emergency braking systems happen across the country. So basically, there's an open question there. in the world of non-safety critical systems, the big internet companies have got very good empirical methods for detecting and diagnosing if a machine learning system is going crazy. I would claim that they are better than us in academia by several years at doing that. But no one, to my knowledge, has able to come up with a proof of safety, even for linear regression, let alone a deep network.
Well, with that, yes, so I'd like to thank Andrew Moore once again, and I'd also like to thank the Arts Initiative for allowing us to have this here and to host the reception up in Studio 1, which is just upstairs. And lastly, I'd like to thank Joe Hogan and the organizing committee for putting together a great event today, and I'm really grateful to them for all their work. So let's thank Andrew again.